Yeah, good morning, everyone. I'm Qiang from RV. Yeah, I will talk about climate change in the Arctic Ocean. The focus on the small scale, meso-scale eddy activity, how it will change and how it will interact with sea ice or influenced by sea ice and impact on sea ice. But we start from large-scale circulation in the Arctic Ocean because that strong linkage between the large-scale circulation and the eddy activity, as we will address in this talk. So the large-scale circulation in the Arctic Ocean is mainly driven by wind. As we see, the climatological mean sea level pressure, we have the Beaufort High, the high sea level pressure over the Western Arctic, the so-called Beaufort High. It drives the Ekman convergence of surface low salinity water, we call it fresh water, towards the Beaufort Dry. And as shown in the upper right figure, this is the freshwater content is considered as an inverse signal of vertically integrated salinity. So this high freshwater content is associated with anticyclonic Beaufort Dry circulation. And because the density in the Arctic is mainly determined by salinity, this can be considered as a pattern of sea surface height in the deep basin area, at least. Yeah, there had been a big change over the last 20 years in the upper Arctic circulation. Again, here as shown by the anomaly of freshwater content. The first big change occurred before 2009. As we can see, there was a big increase in freshwater content in the Beaufort Dry region. And afterwards, in the following 10 years, we can see there was a decrease in freshwater content in the Eocene Basin and the Maklawa Basin. This indicates a strengthening of the cyclonic circulation in the Eocene side of the Arctic Ocean. And at the same time, the total freshwater content in the Beaufort Dry region continued to increase, although the size decreased. In very recent years, we can see the cyclonic circulation further strengthened and extended to the Canada Basin, and the freshwater content in the Beaufort Dry region started to be released. And we can see the increase of freshwater content north of Greenland, and we call this region the buffer zone. This water will release finally to the North Atlantic, but according to my information from people who are doing observation at Strait, they already observed a strong release of fresh water. So we are waiting for a big great salinity anomaly, and different from before, we have a lot of, quite a few times great salinity anomaly event in the past, but at that time we don't have very good observation like the Outline. Now we have that. This can be considered as a natural experiment. We can verify a lot of hypotheses, ideas, how the Arctic freshwater can impact the overturning circulation. And we are waiting for that. Yeah, if you look at this here, the upper figure shows the sea level pressure anomaly associated with each period. We think we can explain these changes from wind changes. For example, the first period we have high sea level pressure anomalies, that means convergence of fresh water. And in the second period, we can see the sea level pressure is neutral in the Beaufort Dry region, but we have low pressure around. That means still a convergence of freshwater content. And further outwards, in the recent period, the AO was in the positive phase, and plus some positive anomaly in the center, which can influence the freshwater export from the Arctic to the North Atlantic, and so on. And we think we can explain a lot of changes with wind, but it's not the full story. If this is the only story, then we'll not show this because the topic's about ocean and sea interaction. There should be contribution from sea ice, that's why I show this. And we try to do the attribution to understand the driver of the recent changes in the Arctic Ocean circulation. I don't show everything about this study, just to address the impact of sea ice. We compare the impact of sea ice with wind. And what we do, we have the control historic simulation driven by real analysis. and the model can reproduce the observed changes in the Arctic Ocean and sea ice. And we do another simulation. In this simulation, we apply climatological thermoforcing over the Arctic Ocean. And then, as we can see in the upper left figure, we can remove the declining trend of sea ice by doing this. In another experiment, we try to remove the wind anomaly associated with this sail pressure anomaly. Here is the change of freshwater content between the sensitivity experiment and the control run. Basically, it tells us the impact of sea decline and the impact of the wind anomaly in this period. The left one, you can see that this is the impact of sea decline. Basically, it redistributes the fresh water from the Eocene basin and the Mackinac basin towards the West Arctic. And this is the impact of wind anomaly. You can see they have the same tendency, but in terms of magnitude, they are quite similar. So we cannot explain just the recent changes in the Arctic Ocean with wind. We should not forget the impact of sea decline. How sea decline can impact the Arctic Ocean? So the left figure shows the difference of surface freshwater flux associated with the sea decline. We have the two experiments. One the control run, one we remove the sea decline. Then we can check the difference in terms of surface freshwater flux. You can see that inside the Arctic, it's almost everywhere is positive. It means sea decline just produce positive freshwater anomaly to the Arctic Ocean. If this only impact, it will not reduce freshwater content in the Eocene basin. So the real impact is from the changes in the moment transfer. The sea decline increases the moment transfer, allow the mean wind. The mean wind we have high stellar pressure over both side region. It try to shift the surface freshwater toward the West Arctic, and the sea decline simply amplifies this effect. That's why we can have these dipole changes. And here, the same experiment now we show here is the sea height anomaly. It's quite similar to the freshwater content inside the Arctic Ocean, but at the same time we can see a reduction of sea height in the Nordic Sea. This is associated with a reduced freshwater export from the Arctic Ocean, the sea ice export. Then the salinity is higher with sea decline, and this altogether we have an anomaly of cyclonic circulation. And further, this can bring more warm water into the Arctic basin. Here, what we see is the temperature anomaly induced by the sea decline. You can see that sea decline draw in the warm water. It warms up the Earth basin, also the Mackinac basin. And this impact of wind, we have the high pressure here. It tends to reduce the warm water inflow. Actually, the observed Atlantification in the Arctic deep ocean is the competition between these two effects. Certainly, another plus is the long-term warming trend of the water itself. In the future, so the decline of sea ice, it will impact the ocean circulation further through increasing the momentum transfer. And we did some sensitive study. We still do the historic simulation in this study, but we try to change the thermoforcing over the Arctic. Everything the same wind observed in the historic period, but just we try to modify the thermoforcing. We can produce different state of sea ice, and we can see that with sea decline, the surface ECMA transport will strengthen. The warmer, the stronger the ECMA transport from the Earth basin toward the West Arctic. And we can see this the salinity transect across Arctic Ocean. The effect of sea decline is to increase the first content because it reduces salinity and increase the salinity in the Earth basin. There's uplift of the Atlantic water towards surface by sea decline. This is the contribution of sea ice decline to the progression of the classification in the Arctic Ocean. Yeah, so I will talk about the activity in the Arctic Ocean, the small-scale circulation. As we know, the rod radius in the Arctic Ocean is very small, and we need very fine model resolution to resolve meso-scale eddies. The model we use is the model that we have been developing for about 20 years. It's called FISOM. Now we are at the second version. The second version we use finite volume method. And the advantage we can do local refinement. In a global context, in global configuration, we can increase resolution in the region where we want to focus. In this case, certainly it's the Arctic region. And we also have the couple model, FISOM as a sea ice ocean component, but the experiment I will describe in this talk is fully based on the ocean alone simulation, not the coupled simulation. So by increasing resolution to 1 kilometer, we can well resolve the meso-scale eddies. It's just a snapshot in the West Arctic. And this is in a moment where we don't know that there was no sea ice. Immediately at the surface, we can see a lot of eddy activity. And the right figure shows the mean eddy content energy at some surface level. I think it's 100 meter depth or 50, I forgot. And there's some thought, if you can see that from observation. Basically, the model in terms of spectral pattern is consistent with very limited observation from mooring. And we can see an increase eddy activity in terms of EKE along the boundary in the West Arctic, also along the continental slope in the Eocene basin. But overall, we know that because of sea ice coverage in the Arctic Ocean, the eddy activity is relatively low. And you can see a very low level of EKE in most of the area in the Arctic Ocean. In the interannual time scale, the sea ice cover can strongly influence the strength of eddy activity. As you can see that in 1 year, in the upper one, in September, the sea ice cover is relatively low. We have relatively strong eddy activity. And in a year, in this example, the sea ice cover, the sea ice area is larger. We have then relatively lower eddy activity. This can be, just a snapshot to give a direct impression. We can do a linear model, try to fit the EKE, eddy content energy in the Eocene basin, to different impact factors. You can see that upper ocean, the 1 to 50 meter depth mean EKE can be mainly explained by sea ice area. But in the deep layer, between 100 meter and 300 meter, it's mainly explained by volcanic instability and stratification. So how the Arctic Ocean eddy activity will change in the warming world in the future? We try to do a future projection. As I mentioned, it's not from coupled model. What we do actually, we try to get the surface forcing from a low resolution RVCM, our coupled model result. We get the wind forcing and thermal forcing, and then drive the ocean sea ice model. And so we first run the model with relatively low resolution, 4.5 kilometer resolution, and it's allowed around, easily to do a 100-year simulation. And then we try, at different period, we try to do slide simulation, interpolate the low resolution model results to the 1 kilometer model configuration, and do a few years. And then these are the results from this 1 kilometer resolution slide simulations. The upper figure shows a snapshot of ocean current at surface and at 50 meter. The lower figures show the result on the same day, but at the end of the century in the SSP 585, the 4 degree warming world scenario. We can see that in December, in the warming world, in the 4 degree warming world, we have very small sea ice cover, and we can see that very strong current at the surface compared to the current climate state, and also we can see a lot of eddy activity. And also we can see a clear strengthening of the eddy activity at depths. And the right figures show the EKE and the barochromic energy conversion rate, also for the current climate and for the future. And we can see that at the current climate, as we have shown that the comparison with observation, we know stronger eddy activities along the boundary, along the topography features. And in the future, also the strongest increase of eddy activity also in these regions. Also, but in the interior Arctic, we also see increased eddy activity, but the magnitude of the increase is smaller in the interior basin. Overall, integrate over the upper Arctic Ocean, the total EKE will increase by about 3 times. This is much larger than we know for the lower latitude. We know in most of the most area of the strong eddy activity region in the mid-lower latitude, according to high-resolution future projection, there will be increasing eddy activity by 50, 60, 70, 80%. But in the Arctic Ocean, it's not just some few tens of percentage, but 3 times. That's because in the current climate, because it cover the base, the eddy activity very low. The right figure shows the seasonality of the energy conversion rate. It's it basically explains the change of the upper ocean eddy kind of energy. But at the same time, we can see the blue bar, they show the surface energy dissipation on the eddy scale. Positive means reduced eddy killing at surface is understandable because in the future, in summer, there's no sea ice, the dissipation is mainly from wind. But in winter, even in the 4-degree warm world, we still have a few months with full sea ice cover. That's why the eddy killing will be stronger. Here is a better explanation. On the eddy scale, in summer or in winter, current climate, or in the future, we can see the surface power is negative. Means eddy will lose energy on this small scale, either dissipated by sea ice or by wind. Just in the case if the dissipation by wind, the magnitude is much smaller than the effect of sea ice. Certainly on the larger scale, in the future, in summer and no sea ice, the Arctic Ocean will receive a lot of kind of energy from wind directly.
Can I just ask a quick clarification question? What measure of dissipation is this? I don't know the term eddy.
Oh, so dissipation means we compute this the surface stress and multiply with ocean current, and we look at the small scale perturbation in that. We do this with cost gradient. We remove the large scale, depending on the scale. You see on the x-axis the scales. At 100 means we remove the signal larger than this. What remains is the power on scale smaller than 100. So the right figure show the spectral pattern at scale of 50 kilometer. And the upper figures show the current climate, and the lower figures show the future. It's clear that in the future, in winter, because of increased eddy activity, you have more energy to be lost, to be killed by sea ice. Although sea ice is thinner, about 1 meter only, but still it's relatively compact. So we have increased eddy killing. So as I mentioned, these are our old work. In high resolution, we can project the future changes of eddy activity at surface. In most of the region, and we expect increased eddy activity except for the North Atlantic because of weakening of AMOC. A very recent study, they show, okay, this based on 110 degree CSM, high resolution simulation, we agree as the surface eddy activity will increase in the future, but they report a strong reduction in eddy activity in the deep ocean below 100-meter depths globally. And actually, this will lead to the overall reduction of the total kinetic energy in the global ocean. So how about the Arctic Ocean? Certainly, 110 degree, you cannot resolve the eddies in the Arctic Ocean. Here we compute in our 1 kilometer resolution simulation the kinetic energy integrated from 100 meter to 1,000 meter depths. The upper figures show the current climate, and the lower figures show the future scenario. You can see that our model predicts a strong increase in total kinetic energy, mainly explained by the increase of the eddy kinetic energy. So there will be increase in the mean current, but the major contribution from the increased eddy activity. Here is the time depth plot. It can better illustrate the change. We can see the strengthening of the eddy activity through the whole depths. Although we see the decrease with depth in the eddy activity, but the signal is discernible until at least 1,000 meter depths. And this is a strong contrast to the global mean. So what's the reason? Here we computed the energy conversion rate from available energy to eddy kinetic energy in the current climate and in the future. You can see the strong increase in the conversion rate, and the right figure shows the conversion rate from mean kinetic energy to eddy kinetic energy. We see that in the current climate, except for along the core of the Atlantic water current, it's positive. In the most of the area is negative, means the energy is converted from eddy into the mean flow. And actually, this will be even stronger in the future. Here is just a static, the integral, and for different depths, the upper ocean, the deep ocean, and the whole upper 1,000 meter depths. You can see clearly see that the increase of eddy activities means because of volcanic instability, and basically the energy conversion to the mean flow somehow tend to reduce the eddy activity, but still the dominant contribution is from the increased volcanic instability. So we go back to the large scale because this is a direct relevant driving forcing, and based on CMU6 result, we have found that, yesterday we talked a lot about Arctic amplification, but by default that's atmospheric amplification. But actually, that's in the oceans, there's similar amplification. The Arctic Ocean is already, and will continue in the future, be warming up faster than the global mean. And as you can see, the upper 700 meter mean temperature, the change, the difference between future and the current temperature. We can see the largest warming is in the Arctic basin, and this is the zonal mean. We can see also clearly see the amplified warming in the Arctic region, but it's not at surface, it's at subdepths. That means it's associated with Atlantic water inflow, associated with the strengthening of the Arctic Atlantification. So this is a transect in the Earthern Basin. The upper one shows the temperature in the current climate and in the future. Clearly, we see the strong warming as we expected from the CMIP result. And here the salinity, and the slow drop in salinity as expected because of weakening of AMOC and especially the strengthening of the strengthening of the water cycle, more precipitation, more runoff into the Arctic Ocean. But the drop is very small, about 0.1 PSU. And this figure shows the potential density. You can see the increase of the density gradient over the continental slope. And basically, this supplies energy for the eddy generation. The lower figure shows the mean available energy transfer rate to the eddy available energy. And you can see the strong increase. And the stratification is projected to reduce below 100 meter depth a little bit. It can also contribute to the increased conversion rate, but the major contribution is still from the increased potential energy associated with the large-scale circulation. We care about the Arctic Atlantification, the warming of deep layer, because this provides heat to influence sea ice phase of melting. But actually, that's not the only story. It can influence the ocean through increasing the energy, increasing eddy activity. And this has a strong implication not only for sea ice, also for like ecosystem, because eddy can strengthen the impact of the increased heat content. So what's the impact of increased eddy activity on sea ice? So this figure, described, we have two simulations. One is a low resolution simulation from 5. It's not eddy resolving, although it's eddy permitting, but we consider this as a reference. And another one is the 1 kilometer resolution. We can resolve the eddy activity. This is the time series of the monthly Arctic sea ice extent. So in the 4-degree warming world, we have about 4 months ice-free. This is consistent to most of the CMIP models. We can see that when the resolution, everything the same, just we increase the resolution locally in the Arctic Ocean, the ice-free period is longer when eddies are resolved. So the sea ice melting is about 4 days earlier, and the freezing is about 13 days later. So we try to find the day when the 1 kilometer resolution simulation start to leave the period of ice-free, and on the same day we find the sea ice concentration in the low resolution simulation. So here is the upper one shows the sea ice concentration. We can see this is the time when sea ice area start to be the cutoff value, 1 million square kilometer. But at this time, on the same day, you can see that in the low resolution simulation, we have already a lot of sea ice. And at the end of the year, the counter shows 15% sea ice concentration. You can see that at the end of the year, at the resolving simulation, Atlantic and Pacific side, they are still connected without sea ice, because it's lower than 15%. But in the low resolution simulation, it's already closed. The gateway is already closed in the interior of the Arctic Ocean. So how to explain this? So it's influenced by increased eddy activity in the future Arctic Ocean, which can be resolved with 1 kilometer resolution. The right figure shows the temperature in the high resolution and low resolution, the salinity. The upper one shows the difference. You can see that with 1 kilometer resolution, the upper ocean can absorb more heat from the atmosphere in summer. And the left figure shows the time series of the total surface heat flux in the two simulations and the difference. And at the same time, we show the time derivative with upper 50 meter heat content. They fit very well. We don't have to do further heat budget analysis because the change of upper 50 meter heat content just can be explained by surface heat flux. Meaning in summer, we see the difference in winter. But here, the real important factor is the summer heat uptake. We can see that this is a pattern of the upper of the seasonal heat flux in summer, and the seasonal temperature actually in the high resolution is lower because more heat is taken downward. And the lower seasonal temperature allows to absorb more heat. It's reasonable. You need the largest temperature difference between the air and the ocean. That's why you can absorb more heat. And this is the September mean difference of upper 50 meter ocean heat content. So the ocean absorbs more heat. This is realized by increased summer upper ocean mixing. This figure shows the difference of the vertical mixing coefficient. This can be explained by the reduced stratification and increased vertical velocity share. And the reduced stratification can be explained by eddy-induced vertical salinity flux, which basically is contribute to the reduction of surface fresh water a little bit. But in both cases, the salinity stratification is still strong. Just leave this vapor, it allows an increase of vertical diffusivity on the level of just 10 to the minus 3. Actually, this is sufficient to allow the upper ocean up 20 meters to absorb more heat. And this heat is released in fall. It delays the formation of sea ice. And we can see that the upwards ocean surface heat flux is stronger with the eddy resolving resolution. And now the surface temperature is higher. And in December, most of the heat already lost, a little bit left. This can influence the winter time development of sea ice. And together with the vertical eddy flux, this contributed to the 4 days earlier opening of the full Arctic Ocean without sea ice. Okay, in summary, on the large scale, sea ice decline can strengthen both the anti-cyclonic circulation and cyclonic circulation of the upper Arctic Ocean circulation, and it strengthens the Arctic Atlantification. On the small scale, sea ice can increase the upper ocean eddy activity. The further development of the Arctic Atlantification will also energize the deep Arctic Ocean in contrast to the global mean trend. And we see that the intensified eddy activity can enhance Arctic sea ice decline, especially it can extend the Arctic ice free season significantly. That is all. Thank you for your attention.
Thank you so much, Qiang. So we have time for questions. Just like yesterday, I invite you to use the mics on both sides of the room. Camille, of course. First question.
I actually have 2 questions, if I'm allowed. Thanks a lot for the talk. My first question is on the last part. You're making an argument that you changed the length of the ice-free season based on thermodynamical interaction. Have you looked at all whether when you're in the higher resolution run, you have some kind of a more energetic sea ice that could also melt for dynamical reason? Or it's really purely an interaction with the ocean and heat content? And should I ask my second question now?
Maybe one after one, I
Okay.
can remember. So I think the main reason is just the heat source. You need the heat, absorb the heat in summer, and it's in the upper ocean. You must release heat before you form sea ice. And maybe there's some dynamic effect, but we need, but whatever, you need the heat source. That's the main reason. First, you need heat uptake.
I agree. I would just also expect that your sea ice is more dynamical, and that could also change.
Yeah, especially if you look at this figure, it's because at this time, we think about the starting day of the you leave the period as free because basically you don't have sea ice still. And I know your study about the inner state when sea ice forming eddy can influence, and I like your recent study, but maybe there's some effect here. But the heat is taken from, I think, is from the ocean.
Okay, and my other question is on the first part, on the attribution of the freshwater content change. You try to decipher between what comes from the wind and the ice decline. But to some extent, these 2 signals, they have some time scale of equilibration. I mean, even if you reduce the sea ice, it will take like a decade to accumulate the fresh water. And have you looked at do you have a feeling whether or not the 50% that you're giving is more of a transient response, or that would be the same thing if you were looking more at the equilibrated response?
Yeah, good question, actually, or good comments. it really depends on the time we set, we try to remove the CI decline signal. What we did actually is to, because we know the CI decline in the last century is relatively small, what we did is to restart the simulation in 2000. And at that time, we keep the thermal forcing climatology of over the last 20 years, I think, last 20 years of the last century. And then we keep this to run. Basically, we compare this state with the historical simulation, the Hanscast, which CS continue to decline. The time scale develops with time, and the signal also changes. If you look at the first 10 years of the end of the simulation up to 20 years, the impact is different because otherwise CI is declining, and you keep the same level of CIs. Certainly, the difference increases with time. And also for the wind, also it's a long time, and the sensitivity experiment is 15 years. We took 15 years just because old publications, they also took the same period. We try to do the same to compare with previous study.
Okay, thank you.
Yoshi.
Yeah. Thanks for nice talk, Qiang. I found it very interesting about the deep water, energetic eddy, more eddies in the deep water. I think you mentioned that it's because of the mean current. Is that right?
Yeah, the Atlantication, basically the potential energy associated with the deep water increase.
Is it because more Atlantic water is coming in, or?
Yeah, good question. I didn't show that. First of all, the temperature is increasing, and secondly, there's a small increase of the Atlantic water inflow in terms of the volume transport. Yeah, that's both contributions.
Okay, thank you.
Yeah, thank you.
Actually, I had a similar question. Could you go back to that slide, please? Sorry, Andy Thompson from Caltech. Energization by Atlantification. I think it was this slide.
This one?
Yeah, that one. Okay, so one quick question. You are in a salinity stratified regime in the Arctic?
Upper ocean, yes.
Okay, so I guess I'm a little bit curious why the salinity and the potential density look so different. Are you temperature stratified in the deeper part of the water column?
So we did try to so first of all, it's associated with Atlantic water, but then it's really the contribution larger from temperature and from salinity. Maybe we could do some quantification by use the same salinity and different temperature to compute the this transfer rate or compute the density. But just visualize this part over the mean part, this region, and it's more comparable to the azo zone rather than the salinity. But maybe we can do this quantification to be sure. Maybe the contribution from salinity in world is underestimated. But anyway, it's associated with Atlantic water because the depth is Atlantic water.
Okay, I think that's helpful. Because the picture I had sort of always had in my head was that the freshwater content was increasing the baroclinicity, right, as you have more sea ice melt or runoff from land.
Yeah.
But then that also increases the stratification.
That's mainly for the Bogota region, not the Eurasian basin.
Okay.
For the second is upper ocean, not because in this depth, as you can see, salinity actually, freshwater is just upper 50 meter, low salinity. Below is Atlantic water property.
I see. Okay, so that's helpful. A very different mechanism from what we're seeing in the Beaufort.
Yeah, if you look at the property, this low salinity will be much deeper.
Okay, thanks very much.
I have a question regarding the eddy activity. You showed your FISOM-2 simulations showing then an increase in eddy activity in the Arctic in the late, around 2100. And you connected that to loss of sea ice, and it's visible over the sea ice area, but there's also an increase, at least from the figures, in the parts that hasn't been sea ice covered even in the present day, in the subpolar North Atlantic to the extent that you could see it. That was one thing that I was wondering about. So how much do you know what's sea ice and what are potentially other causes? And then later you showed from the Beach et al. 2024 plot a global eddy activity increase over the 100 years. and the Arctic didn't stand out at all. Can you reconcile those two figures?
Yeah. I hope I understand your question correctly. So I think maybe the second one, and so you are talking about this figure.
Yeah, you had another one, I think maybe before. Yeah, I can't remember exactly where. Yeah, I think it was before.
What?
Yeah, we could. Yeah, so this one actually go forward.
Forward.
So yeah, this.
Oh.
Okay, let's take it over the break. Yeah, it's too hard probably to figure out. But yeah, let's take it over the break. No, this was before the eddy killing. Yeah, this one here. No, it wasn't that one.
But your second question is about this.
Okay, so this one, I mean, the Arctic doesn't seem to stand out here in at least on the global.
This is our CMIP6 contribution from RVCM. Right. We have only increased resolution along the mean current. Right. It's really, we designed the mesh, the model resolution, according to separate observed system height variability. Okay. Where the system height variability from observation higher, we increase the resolution locally. Okay. And certainly we cannot resolve Arctic Ocean.
So you're not resolving
because we need 1 or 2 kilometers to resolve. Right. This cannot be done in the framework of CMIP6, even CMIP7. We cannot do. Okay, and so our CMIP7 resolution will be 5 kilometers for the Arctic, not more.
You cannot actually address the question. And then if you go a couple of slides before then, for your own simulation, the FISOM, this one here, I think it's this one here. Yes, that's the left panel. If you compare the upper and the lower plots, you have eddy activity increasing not just in the, you also see it in the Greenland Sea and in the Nordic Seas region. So I was just wondering whether you have sort of a reference where you basically say, well, this is where eddy activity potentially increases even in ice-free regions versus the extra part that you see, of course, in the sea ice-covered regions.
So we focus on the Arctic Ocean, and our high resolution 1 kilometer resolution actually stop as a boundary. Actually, it doesn't mean that here the eddy is lower currently or in the future. Just resolution drops, as this is the boundary. Yeah. But anyway, we focus on the Arctic Ocean as start from the gateway, which is what we analyzed, and basically our quantification of the energy conversion rate is also for the Arctic interior, yeah, because the seasonality actually somehow answers the impact of sea ice, and because the sea ice reduction actually in fall and in winter, in early winter, there will be strong sea ice reduction, and you can see the strong increase in the activity. This is not absolute value, but the magnitude of the increase. So somehow it shows also similarly the impact of sea ice.
Okay, thanks.
All right, I think we're going to move on to the next talk. Thank you so much, Qiang Wang.